right, let's see here. Okay. Okay. So, yeah, let's get started today. So what are we going to do today? And the answer is asymptotic analysis. But before we do that, let's just do some other announcements. So basically, the multiple choice questions for exam 2 have been posted. They're due on Sunday as well. Remember that you have 2 hours to complete them once you start. So don't walk away, okay? Don't leave it. Make sure you do it all in one sitting. My estimation is that it should take maybe 30 to 45 minutes to do. That's my estimation. But I've given you 2 hours because you have way more time than you could possibly hopefully need on it. So that's what I've done. Okay. What else? Yep. Okay, so what else is there to say? I guess not a lot else. We'll release Project 3 maybe this Friday, Saturday, at some point whenever I finish it. I have a number of things that I have to do before I finish writing it up, so we'll see. It might be Saturday. And that'll be the last project. And then the only other assignment is the final exam. Okay, so, all right, I think that's just about it. So let's begin asymptotic analysis. So what is asymptotic analysis? So project 3 is always a recursion project. The final exam is going to be just like all the other exams. It's going to be, basically I'll just release it and then you have as much time as you need to complete it up until 12/16. But we'll deal with that once we get there. Okay, so let's start with asymptotic analysis. And so basically asymptotic analysis, the notion of asymptote really in this case is asking what happens to our algorithms as we increase the input size to, say, n, which n is going to infinity, right? And so that's the question, is basically what happens to our algorithms as we increase the input size to a very large size. So we're not concerned with the performance of an algorithm, say when it's say it's operating on n equals 10 or n is even equal to 100 sometimes. We're usually considering like n is equal to 1,000, 10,000, or even 1,000,000. And so of course you might ask, like, what does input size mean? And of course that depends on which algorithm we're talking about. But in our case, it's kind of dependent on, for instance, the so if we're talking about sorting algorithms, I think sorting and searching algorithms, any algorithm like that, data storage algorithms, generally for sorting, searching, accessing, basically anything like that storage, we're always concerned with the number of things we stick into the structure, which generally is either a list or a dictionary or some more advanced data structure. So that's generally the way that we look at this stuff. So, okay. All right. So let's just do some examples of calculating like the big O of a function, and then we'll go back and maybe do a little bit of theory, and that's what we're going to do. So in previous semesters, we made this stuff way more technical, and I realized that in previous semesters, the performance here was I'll say like off scale low in general. Whenever we gave the final exam in this topic, basically no one got very much on it. It would just destroy everyone. So I'm gonna try it. Here's the new approach, right? Right. So we're gonna do this way more informally. Hopefully you'll get something out of it this time, whereas I think in previous semesters we were definitely way too theoretical. So let's try to get something out of this. Okay. So let's look at our previous thing, which I think is here. So let's look at our bubble sort algorithm just for a little bit. And please don't say it. Okay. So, where is bubble sort? Wow, bubble sort's way up here. So let's not look at this bubble sort. Let's look at the simpler version of bubble sort first. And I'm just going to do an example of how to compute big O here. So here's the example of how to compute big O on a function like this. Actually, maybe what I'll do, I have an idea. Let's snip it. And then let's go back to Inkscape. I think you can just paste, right? There we go. So let's look at this algorithm and just think about what we're doing here. So we have a loop here, right? And how many times does this loop run? Right? Let's this loop, wait, what? Just set it to white. Runs, say, len of a list times. Right? And now you might be like, well, how many times is that? Well, I don't really know how many times that is. It's just however many elements there are in the list. So that's how many times this loop runs. And then here, this loop runs the same, right? It's exactly the same. And at first you might say, well, what about that -1? Well, just don't worry about the -1 right now. I'll explain in a minute. And so then finally, what's the cost of this line here? So we see that this is an A list J and an A list J plus 1. And so we're accessing two array elements. So basically the cost, let's say the cost here is 2, right? And maybe it's, say, 3 for the comparison, right? You have to do 2 accesses in a comparison. Let's say that the cost here is maybe 2, right? Because it's an access and then an assignment. So, right, access, assignment. So that's say a cost of 2, maybe. That's right. That's why there's that -1 on there. And then let's just say, okay, these are all the same. These are all cost 2 because they're accesses and assignments, right? And then this is maybe, I don't know, cost 1 or 2, who cares, right? Well, I haven't really told you yet, right? Just try to go with it. Maybe cost 1 because it's return. So now my question is, what is the total cost of this function, right? And you would say, okay, let's let len of a list minus 1 equal to n, okay? Or you can just let a list being n, like this. And so then the total cost of this function is basically equal to n times n. And why is it n times n? It's because you're running n loops in the first thing. So you're running something n times, and then you're running something here n times, and then you're running this if statement. And let's assume that this if statement executes most of the time. And then the last return statement is just a +1 at the end. So here the cost of bubble sort is going to be equal to n squared, well, n times n, I guess, times, and then what's the constant that pops out here? It's, what, 6, 9, so we got 9 times this plus 1. Okay, so this is why we generally call bubble sort an O of n squared, and I guess maybe I'll use LaTeX for this. Yep, I mean, basically, that's exactly right. The cost is some proxy for the number of operations that we're doing. And so what I'm going to say is that this is an O of n squared operation, or function. And you might say, well, what about this 9, and what about this +1? And so here's the rule for big O. It basically ignores constants, and it will also look at the highest order term, basically. And so what do I mean by it ignores constants? What I mean by it ignores constants is, well, what if I had said, instead of this is a cost 2, what if I had said that this is a cost 3 operation, or this cost 2 operation, or whatever? The thing is, it wouldn't make any difference except it would change this front constant here. And so big O ignores those constants, and it looks at the highest order term. Now, you see this term down here, this +1, is a lower order term because it's only it's a constant term there. Well, I should say it ignores constants of the highest order term. And you basically only look at the highest order term. And so what I mean by, and so basically that's how you would get that this is an O of n squared operation. So that's how bubble sort is usually called O of n squared. Okay, so yeah, what we're trying to do here is we're trying to calculate well, okay, I mean, if you want me to define it, but I'm trying to avoid defining it, right? So, here's the rule for big O right here. So the idea of big O is it gives us an estimate of the amount of time that our algorithm will take. If there's 2 of the largest term, it is ignored. Well, so if there's 2 largest order terms, you usually add it together to get 1 largest order term, right? So if you have like something like, I don't know, if you have something like 3n squared plus 4n squared, that's going to be equal to 7n squared. Right, so then that would be the highest ordered term. Oops. So basically, if you have something that has a square on it, and you have something else that has a square on it, and then you just add them together, and that'll get you the highest order term. Big O ignores the constant on this, so this is also O of n squared. All right, so let's do another algorithm to try to compute the cost of its runtime. Let's look at selection sort, maybe. Sure. And maybe what we'll do, at least for this time, what we'll do is we'll delete these two lines here because they're not actually part of the selection sort. They're just there to make us see things. So let us do that. And then here, let's copy it. And paste. So let's look at this algorithm. So basically here, we want to compute the total cost of the algorithm. And so in order to compute the total cost, we know that here it's going to run the number of times in the list. So basically here it's going to run n times, for n is equal to the length of the list. Yeah, basically, for execution time. So big O is a way. I'll do this one and then I'll answer that question. So basically here, now we have to ask ourselves, well, what's the cost of the find min index function, right? So then it's going to be the cost of the find min index, right? And then the last one is the cost of swap. Right, and so basically our total cost is going to be n times, right? So selection sort is going to be equal to n times the cost of find min index plus the cost of a swap. Okay? And so, and plus maybe 1 for the return, but we can ignore that for now. So first we have to compute the cost of the find min index and the cost of the swap function. So let's copy paste both of those. Sure, let's do that. Let's copy them and paste them into the thing. So now we have a subproblem. We have to compute the cost of these two functions. And so the cost of swap here, basically this is, you can call this like 1 or maybe 2 operations. It depends how you think about it, right? It's either an access and an assignment, or it's just an access and an assignment. So maybe we'll call it 2. The cost of this is 2. The cost of this maybe is 2. Let's just say that the cost of all of them are 2. So the total cost, is equal to 6, right? And now what if you had said that the cost of swap was equal to 8? Would that be okay? Yeah, it's fine. Like, the point is that we know, what do we see by doing this? We see that the cost is 6. And what does that mean? The important thing about that cost is that it doesn't depend on the list size, right? That's the important thing. Yeah, we care that it's a constant. We don't really care exactly about the constant that it is. Okay, so that's the point here, is that we care that it's a constant. We don't really care exactly what constant it is. Okay, so now let's compute the cost of this function. So this is basically an assignment or something. We'll call that cost, let's just call that cost 1. And then here we know that whatever happens in this loop is going to happen n times. And then it's going to be n times the cost of an if statement, which is, say, I don't know, 1 or 2 maybe. and then the assignment, right? So basically, the total cost of this function is 3 times n, right? That's equal to the cost of find min index. And again, we don't really care about this constant 3. All we care about is that it's some constant times the length of the list n. That's the thing that we really care about. This is what we were trying to calculate here. So now we can go back and calculate the total cost of selection sort, right? Which is n times the cost of find min index, which we can now replace by 3n, and the cost of a swap, which we can now say is 6. Plus there's some return statements, so we can add in some plus 1s or whatever. Maybe if we add in the plus 1 here for the return statement, that'll show you what I mean by lower order terms. And so now overall, when you FOIL all this out, or whatever you want to do with this, right? So this is 3m plus 7. So in the end, this is going to be, what is it going to be? It's going to be 3n squared plus 7n plus 1. And so let's find it. Here we are. Whoops. Made a capitalization error. I don't know why it always likes to put it right out of view. But anyway, this is what the function is. So this is our cost of selection sort. So now, basically our rule is, remember the rule for big O, we drop all but the leading term. So basically n is always smaller than n squared. So we're going to drop n. And 1 is smaller than n squared, so we're going to drop 1. And so what we're left with is just 3n squared, right? That's what we're left with. And so then the next big O rule says ignore the leading constant, which is just going to get us n squared again. Okay? So now overall what we get to say is that this algorithm is also O of n squared. Okay? So that is the complexity of this function. So let's actually do some examples and let me show you what I mean by the complexity of the function or whatever. So yeah, this is a good way to do it. So let's step off at this point and actually do some examples about things. So let's import, I think time has it, or maybe, is it time or time it? I think there's a time dot get process time, or process, yeah, that's what we want. So, okay. So now let's do a little test. Let's do a bubble sort time test. And so let's time this thing. And let's do a few tests. So for I in range, say 5. Let's generate some random lists. Okay. Or yeah, let's generate some random lists of size n. And so now what we're going to do is we're going to do bubble sort simple on the my list. And we're not going to output the sorted list because we don't really care about the sorted list. All we care about is the time is, the time was end minus start. And we're calculating this in nanoseconds, right? So nanoseconds is 10 to the, what, minus 9th seconds. So there's a billion nanoseconds in a second. We could calculate it in some other unit, but I mean, this is fine. I mean, I guess we could also just do process time, I think. Let's do process time nanoseconds, because I think that's That's good at least to see small times. And so here what we're going to do now is let's call the bubble sort time test on, say, a list of size 10, and then on a list of size 100, then on a list of size 1,000, and then finally on a list of size, let's see, 10,000. Is that going to be too big? It might be, but let's see what happens. Let's see what happens. I think it'll be too big. So here we go. Okay, well that didn't really tell us very much. Let's just use process time and see what it tells us then. So, yeah, let's hope that it gives us some better results for the next one. It's giving us a lot of zeros. That's unfortunate. Ah, well, I guess that's fine. This is fine. Once this finishes, I'll be able to explain to you what's going on here. I guess it's going to take about a minute because that's what this is going to take. So maybe while it's doing that, I'll explain what I mean. Yes. So if we look at the times that it's taking, right? This is on a list of size. I'm guessing this is on a list of size 10,000 here, and that this is on a list of size 1,000. I think the resolution is just not good enough to get us times on the lists of lower size. Maybe we'll have to rerun this test. Yeah. So these were on lists of lower size, so it's a little hard to tell. Let's say time. But the point is that what we see here, let's see if we can make this a little bit more accurate. So we see here that the time was 0.14 seconds, 0.14 seconds, 14, 0.125, 0.125. And then here, you notice that it was 13 seconds, 13 seconds, 13 seconds, 14 seconds, 14 seconds. So it's at the upper end of 13, at the lower end of 14 seconds to do a list, to do 5 random lists of size 10,000. And it's at something like that seconds to do a list of size 1,000. So what Big O tells us, and this is how we know that Big O is kind of getting the answer right, is that if for a list of size 1,000, it takes let's average it out and say 0.135 seconds, right? Then for a list of size 10,000, we expect it to take, well, so remember that it's O of n squared. So being O of n squared, 10,000 divided by 1,000 quantity is equal to 10, but quantity squared is equal to 100. So we expect that the algorithm will take 100 times as long on a list of size 10,000 as it did on a list of size 1,000. Okay, that's what we expect. Okay, and then we look at the calculation. We look at the calculation of the exact times and we say, oh, look, it's 13.89, 13.96, 13.65, 14.28, 14.02 approximately. And so is that about approximately 100 times this, right? 100 times this is what? Our estimate was 13.5. And so it's a little on the low end, maybe, a little on the low end, but you see that it gave us kind of an estimate for the time that it was about to take on this function, right? And so that's kind of the reason why we do these Big O calculations, is to determine, like, for instance, if you were going to run this on a size, say, if you're going to run this on a list of size, say, 10 million, and we expect that, and we know that the average is approximately 14 seconds on a size of list 10,000, and we divided this thing by 10,000, and then we squared it, what would we get? We would get something on the order of, well, let's calculate. Let me pull up Windows Calculator because that's what I'm going to do. So 10 million divided by 10,000 is 1,000. Oh, wow, that's shocking. So then you're going to multiply that and square that. And so the problem here is that this is equal to, I should have just done that in my head. I don't know why I didn't do that. That was nonsensical. Okay, so that was 1 million, right? So the estimation here is that it will take 1 million times as long to do a list of size, and to by do I mean sort, a list of size. That it's one of the things. You know, it's a sort of list of size 10 million, right? So, and if we know that it takes about 14 seconds, right, then it's going to take about 14 million seconds, which is approximately 0.44 of a year to do. So that's why we don't assign, for instance, if we ever give you a sorting algorithm, we will never give you a bubble sort that has to sort 10 million elements. That just won't happen because no one has the interest in waiting a quarter, not almost a half of a year, right? It's like, what is it exactly? I think it was like 162 days it'll take, a straight computation, just to complete this operation. And so that's why O of n squared sorts are not terribly good, right? They're really easy to understand. They're nice. They're simple. They're good for small problems. But you see that as soon as the problem size gets large, that is the whole point, right? And so basically, this is the real true secret point of Big O. Big O is basically a way to, if you know it's n squared, you can take the two sizes, you can divide them, you put them into this and square it, and then you get the ratio of the times that it'll take, right? There is no way from Big O, like Big O doesn't tell you how long an algorithm will take, right? Because it's dividing by all those constants, it's doing all the forgetting of the constants. What it does tell you is it tells you how much, what ratio of time it will take based on increasing input. So basically, what Big O of n squared tells us is that as we increase our size of our data set, the amount of time it takes should increase with the square of the size of the data set. So that is what an O of n squared algorithm does. Okay? All right. Well, so you notice here that I divided by 1,000 here because I knew my baseline here was the calculation that it took 0.135 seconds, right? It took 0.135 seconds for a size of 1,000. So to come up with my estimate, I just divided by the time that we actually computed by just having the algorithm run, right? That's what we actually did. Okay. All right, so let's do this now, and we can call this sort time test instead of bubble sort time test. And we can plug in selection sort. Selection sort, way cool. Oops. It still doesn't like it because I think I need to change this to now sort time test. There we go. So now let's run this one. Let's see what pops out. Blech. Okay. Actually, let's So, okay. And here's where you start to see a little bit more interesting stuff. I changed it from process time to just time to get us a little bit better estimates, at least in these really weird times. So remember that selection sort is also an O of n squared algorithm. So we know that as the time increases, right? The time was 0 for here and the time was 0 for here. But you notice that for the size 10 and size 100, there's no way to tell exactly because it happens so quickly that, except for this one, it didn't even count anything here, right? And so this time might be slightly garbage, so let's just ignore this one. But let's pay attention to the ratio between these times and these times, right? This is what Big O is really talking about. It's talking about the ratio of times between this and this. And so you notice that selection sort performed faster than bubble sort, at least the simple version of bubble sort, right? But you also know that because it's an O of n squared algorithm, you estimate that it's going to take approximately 100 times as long to perform a list of size 10,000 as it did a list of size 1,000. And so you see here that it did actually take that long, because here it took 0.04 seconds to do a list of size 1,000, 0.045, 0.043, 0.041, 0.042, right? And maybe if you're rounding, you'd call this 0.042 as well. So it's rounding to around 0.3, 0.35, something like that. So we would estimate 0.43, so we'd estimate something around 4 seconds maybe. And yeah, I mean, that's basically how to think about it to some degree. And so look at it here, right? We see that here it took about 4 seconds, 3.95, which is about 4, 3.88, which, so it's actually, it's doing a little bit better than that's right. So yeah, so this takes this amount of time. Okay, cool. And then, of course, if you actually wanted to do some really, really horrible thing to it, we could always do something on the size, maybe 100,000, right? And now, the problem with this, and we might only, while I'm talking, we might let this finish maybe 1, because it's going to take a while to do this, right? Because how long would you estimate? It's going to take approximately what? Let's calculate. So it's going to take, if it takes about 3 point some seconds, right, 3.8 seconds to do that, it's going to take 380 seconds. So it's going to take approximately 6.3 minutes, so 6 minutes 20 some seconds. Yeah, so it's going to take a lot of seconds, right? It's going to take about 5-6 minutes to do a single one of these. Okay? So in that time, let's ignore this and look at quicksort. Okay, so quicksort is an interesting one because we'll have to think about it. Oh, it's actually almost too big. I might have to just temporarily delete these constants so that I can copy it. Or, I mean, not constants, what do you call them? Comments. Comments. There we go. And so, now let's put the comments back in. And now let's make this bigger. So remember, we have to wait a while. So let's go back to our Inkscape. And let's do some calculations for quicksort. And let me show you how a recursive function works. Right? So when you're calculating big O over a recursive function, you have to do something a little bit different than you have to do it for the other sorts. Because here, you look at the thing and you say, okay, you know, what are the costs of this function, right? The cost of quicksort is equal to, on size n, right, is going to be equal to n plus, well, you know, Python limits the CPU usage, so it's really not doing a whole lot right now. So, but then here's the thing, right? So you get O of n, or I should say you get about n operations from this for loop, right? You can even say 3n, I don't care, right? You get about n operations from the for loop. And then, what do you have here? You have this list concatenation, but then you have the real cost is the cost of quicksort on this less list, plus the cost of the quicksort on the greater list. And so this leads me into the best case and the worst case analysis for quicksort. So let's talk about what makes quicksort do the best and what makes quicksort do the worst. So the best possible thing for quicksort is that it divides the list in half each time. Okay? That's the whole point here, is that if it divides the list in half each time, then we're happy. Okay? And let me show you why we're happy. We're happy because we end up getting a summation. Let me show you the summation. We get, well, let me show you what we do. Is basically if this is n over 2, and say this is n over 2, right? This is our best case analysis. Then we can then say, okay, cool. So now this cost of the quicksort is equal to 3n over 2 plus the cost of quicksorts of n over 4. So I'm gonna shorten this to 2 times the cost of quicksort n over 2, which is then equal to 3n plus 2 times 3n over 2 plus the cost, let's see, yeah, plus 2 times the cost of quicksort on, say, n over 4. Again, assuming the best case scenario that it divides in half both times, right? And so this is what you're going to end up getting. You're going to end up, what's going to end up happening is something like this, where every time you go through a quicksort, you're going to see that this is 3n plus 2 times this, this. But instead of cost of quicksort of n over 4, it's going to be 3 times cost of quicksort of n over 4, so 3n over 4 plus 2 times the cost of the quicksort on n over 8, right? And then you're going to do it again. So it's going to be 3 over 8, or 3n over 8, plus the cost of the quicksort on n over 16, etc. And this will just keep going forever, right? Now, let's actually look at this a little bit. So let's look and think about this. So this is 3n plus 3n plus, what is this? 3n over 2 plus 3n over 4. So what we're going to end up with is the actual numbers we're going to end up with is, and so remember what's going to happen eventually in quicksort. Eventually it's going to terminate, right? Eventually it's going to terminate. And so the question is, how many times is it going to have to run before it terminates, right? And so the answer to that question is that basically if it's going to divide in half each time, then we're just looking for the time when n divided by 2 to the k, or maybe 2 to the t times, is equal to or approximately equal to 1. And by approximately equal, I just mean it's somewhere between 0 and 2. And so how do you find the solution to this? Well, basically what you do is you just take the log base 2 of n, and that'll tell you the number of times that the thing will run. Right? That'll tell you the number of times that this division process will run. And then each time it runs, right? Each time it runs, you get a contribution of what? Right? The contribution from each time that it runs is approximately O of n, right? And the O of n comes from the, look, it finished. So, and the O of n comes from the fact that there's this for loop here. That's what's generating the O of n, okay? And so every time you run it, you get an O of n, and then it splits into 2 subruns, and it splits into 2 subruns, and it splits into 2 subruns over and over and over and over and over. But eventually what you get in the end is that you run this splitting process log base 2 of n times, and the total contribution each time is an O of n process, right? Therefore, the total complexity of the function is O of n log n, where Lg of n is equal to the log base 2 of n, right? So that's the idea here, okay? So it's kind of complicated to calculate the the efficiency of a recursive function like this. You have to do some trickery. You have to think about it a little bit. But the point is that when you do calculate the efficiency, you're going to see that it's about O of n log n. So, we're not going to let this run to completion, but we do see, right, 300, my estimation was approximately 380 seconds. And so we see that about 368 seconds was the amount of time that it took, right? And so we see that here, because this is an O of n squared algorithm, it takes 100 times as much time to run it on a list of size 10,000 as 1,000, and it took about 100 times as much of time to run it on a list of size 100,000 as it did on a list of size 10,000. So at this point, we are going to kill it. Sorry, little algorithm, we cannot let you finish because you will take forever. So now let's put quicksort in the mix. Let's do some timing on quicksort. So let's do a little bit of estimation. So basically, let's do the estimation of the amount of time, the ratio of time that it'll take between 1,000 and 10,000 runs. So the difference between 1,000 and 10,000 runs is going to be it's going to be basically 10,000 times the log of 10,000 divided by 1,000 times the log of 1,000, right? That's going to be the ratio. So now we just have to ask ourselves, well, what are the logs of all these things? And so as it turns out, 10,000 divided by 1,000 is 10. The log of 10,000, I guess we can just do it with natural logs. It's about the same. Actually, it's going to be exactly the same. That's the secret, because of log base change formula. Divided by that, divided by the log of 1,000. Whoops. No. So it's going to be about that. And we see that if we do it with natural logs, it's going to be the same. Right? It doesn't matter what base you do it in because nicely this is actually the log base change formula, so it's going to be invariant. So time's approximately 4/3, right? Because that's going to be what the log is. So it's going to be approximately 13.33 times the amount of time, right? And remember that for an O of n squared algorithm, it was about 100 times the amount of time. But for O of n log n, it's about 13 times. So now let's do our actual calculations and see what happens. And so I'm going to increase it now. I'm going to be really brave. I'm going to put in size 1 million as well. So watch this. Watch this. Hopefully nothing crashes. Boom. Nice. We have a good set of times, I think. Okay. So, let's look at the times, right? Let's look at them. So this time, let's just admit that any of these times are probably garbage. So let's not look at this time, right? If you notice here, this seems to be kind of close. Like these times here versus this time here, it doesn't exactly match up. But I bet if we had to figure it out, the actual like time intervals that it counts in, the actual amount of time that it allows per tick, is approximately this. So that's my guess here. That's why these are all 0, because it came in under the tick. And here it came in like close to the tick, so it got counted. And so that's what my guess is here. So let's ignore the size of 10, the size of 100. Let's go right to the size of 1,000. And what do we see? It's very close again to the tick size, right? It's 0.00099. So it's basically within the margin of error. It's about 0.001, right? 0.001. But it's a little hard to tell because, as I was saying, this is probably around what the actual tick size is. So if that's when the size cutoffs for time is, then it's going to be hard to see. But anyway, so let's multiply 0.001 times 13, and we get 0.130. So we see that it's a bit of an overestimate here. But I think that can be explained by the tick size of the clock. So let's ignore this one as well, right? It's about half of what it should be, so maybe there is some issue, maybe, who knows, right? But let's calculate the difference between size this and size this, right? So we notice that here we have 0.007 or 0.008, so we have a 0.006, 0.02, 0.076s, a 0.008, and a 0.092. Let's average those together. Maybe it's around 0.75, 0.0075, right? And then what I'm going to do here is I'll multiply that by approximately 13.3. And so that should give us approximately, right, 0.99 or maybe 0.1, something in that range. And so so what do we see? We see that it's actually, Quicksort is actually performing even better than the kind of raw estimation, right? It's actually kind of getting more towards just a factor of 10 than it was a factor of 13. But it's, again, big O is a little wiggly, right? You know, these are estimations on the time. These are not precise calculations. So let's see how it does. Let's see how it does between the size, you know. So let's estimate here 0.73, 0.7, 0.66. Yeah, let's just estimate the average 0.82 plus 0.77 plus 0.66 plus what did I get the 82? Oh, there's two 82s. Okay, divided by 5. So let's estimate that is our time divided by 10, so it's actually correct. Multiply it by 13.3, and we get an estimate of approximately 1 second, 1.01 seconds. I guess I can. I mean, I can just send out the Inkscape thing that I made. Okay, so we have, what was it, 0.76 seconds or so? And let's actually calculate the average now, 0.91 plus 0.88 plus 1.09 or whatever, plus 1.052 plus 0.791, and divided by 5. Of course, it's going to come out slightly better, actually. So even this is coming out, I think it's mainly because of this one, it's coming out better than even our expectations. But you see that it's not so far off, right? It's like a factor of 8 or 10 or 12 or something in there. It's not exactly a factor of 13, but it is actually doing better than our expectations, right? So that is an example of how Big O can be used to estimate. It doesn't give you exactly, but it gives you a ballpark estimation for how long an algorithm will take. And so it basically tells you, like, the important thing about Big O is not like, is it going to give me an exact answer? Will it finish in exactly 13.2 seconds? The main use of Big O in real life is to ask the following question. Will this finish in the next second, hour, day, year, lifetime, and lifetime of universe? Yeah, I'm going to choose to say only that there probably will be. Maybe I'll give it out soon. I don't know. I've been so unbelievably busy at every second that I haven't written it. It's a low priority quiz for me. Okay. Yeah, I mean that's the. I mean, that's also a good thing. So the last thing I want to do is that's actually been asked before, so I'm gonna kind of ignore it. Okay. Okay, I want to talk about merge sort just a little bit. So what merge sort does is it splits a list in half, and then it merge sorts the two halves, and it splits the list in half and merge sorts the two halves, and splits the list in half and merge sorts the two halves. So let me show you how that works. Let's write a merge function. what A list and B list are, so we're going to assume that A list and B list are sorted, okay? And so we have to basically combine those two lists by basically choosing who is the elements and just kind of merging them together. So basically what you want to do is you want to say A index equals 0, B index equals 0, while A index is less than the length of A list, and B index is less than the length of B list. No, length of B list. There we go. Okay. Then what we're going to do is we're going to say if A list at A index is less than B list at B index. Let's say merged list equals empty list. So what we're going to do here is we are going to say merged list dot append. What is it going to append? A list at A index, and then A index plus equals 1. And then else, merge list dot append B list B index plus equals 1. So what is this going to do? This is basically going to go through the list, and it's going to throw in everything in its proper order, right? And then at the very end, there's some cleanup that we have to do, because sometimes the lists won't be perfect. So it won't be A, B, A, B, A, B, A, B. It'll be like A, and then B, 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 B. So we need to say while A index is less than the length of A list, we can do this. And then while B index is less than the length of B list. And then copy paste this. And that cleans up our function. And then we can do return merged list. So actually, if you notice, this is an O of n operation. Why is this an O of n operation? It is because, if you look at it, it goes through both lists once, right? That's what it does. It's like a big for loop, except the for loop has like two indices where it's like incrementing one, incrementing the other, incrementing, right? It's basically keeping track of two things. So maybe you can call this like O of 2n if you want. But basically this is an O of n algorithm. What this does is it takes two lists and it merges them together. So let's comment this, or let's put this into a time test function. And then let's just let me just show an example of merge on, say, 1, 2, 3, 6, 7, or 9, 11, or something like that. And then here, let's do 2, 3, 5, 7, 8, or I keep wanting to hit 8, but I miss and then hit 9, 10, right? Now, technically, the lists don't even have to be the same length, but, who cares? So let me just show you what merge does here. So what merge is going to do is, you see what it's going to do is it's going to take 1, then it takes 2. Actually, I think it takes this 2 first, but it doesn't really matter. It takes this 2, then it takes this 2, then it takes this 3, then it takes this 3. Then it takes the 6, it takes the 5, the 6, the 7, the 8, the 8, the 9, the 9, the 10, and then that one's done, and then it'll do 11. And so that's how merge works. Merge is going to take two already sorted lists and make a bigger sorted list, right? Because you can't just alternate the elements, because you see that here, if you just looked at, say, this element, it's bigger than this element, but like this element is the same, and then this element is smaller, and etc. So it's hard to, you can't just do an AB merging together. You have to do some kind of comparison where you're checking each one before you put it into the merge. So merge sort is pretty cool. What it does is it says, if the length of a list is, they definitely need to be sorted, otherwise it'll produce garbage. Yes. And then what you do is you basically take two different slices. There's your slices. All right, we divide the list in half. And then what we do is we get the full merge is equal to merge of, what is the full merge of? Merge A and merge B. And then we return the full merge. And so here, why don't we actually just print out all the stuff that's happening? There we go. And now let's run it and hope it doesn't crash. Because I have done not much testing on this thing. Let's see. Should this work? Okay. Let's merge sort some stuff. Let's make a merge sort test. I think we can just kind of repurpose the quicksort test. So I want to test it out to make sure it works before we do anything. Sure, let's make it, yeah, so for things in size 20, and all we have to do here is just call merge sort rather than quicksort. And I think that's it, right? And then we, instead of doing this, we'll just call merge sort test. And now let us run it. So here's the original list. And so you see that the first thing that happens is it looks at 51 and 96, and it puts them back in the same order. Then it looks at 30 and 82. Is that right? Interesting. Oh, here's the 76. Okay, so it was some even odd business. So now it looks at 30 and 82, and it puts them in the same order. And then it looks at 76 and then 30 and 82. And what that does is it will then, this is the result of the merge operation here. Whoa. This is the result of the merge operation, right? Because it's merging 76 in with these two, so it sticks 76 into the proper place. This is the result of the merge operation on this much. And then it does it again, right? It does this merge sort on the next few elements here. And then it prints it all out. And then finally we have about half the list sorted, right? This, I think up till this point, is about half the list sorted. And then it does it again on the other half of the list. And then finally it prints out the full sorted list. So basically the point here is that what it does is it divides it in half, it sorts both halves, and then it combines them with merge. So that's what it's basically doing. It's splitting it, it's sorting it, and then it recombines it. And so I'm going to claim, right? I'm going to claim that this... Actually, let's pretend we don't know how fast this algorithm runs. And so let's run the time test on merge sort and see what happens, right? Actually, I'm going to take the 10 out because it never produces any results. I don't even think the 100 ever really produces any results. So, there we go. That fixes that just a little bit. Let's make a sort of size 10 million. Okay, there we go. Now let's time test this thing. All right, let's hit it. Oh, first, very important. Let's remove this print statement. Otherwise, if it wants to print as many times as it's about to print, things will definitely explode. So, okay, let's run it and see. That's 100,000, so a million should take, what, about 6, maybe 7 seconds? So, cool. So let's look at this thing and estimate the running time of this thing. So remember that our multiplier for the running time being O of n log n is approximately 13. So I would say that it's pretty clear that the average here for 1,000 is 0.004 seconds, thereabouts. If we multiply this by 13.3, we get about 0.532, which looks remarkably similar to approximately the average here, right? Which if we then multiply it again by 13.3, oh, it actually overestimates a little bit here, 0.70 this. So, okay, it overestimates a little bit here, but, okay, fine. But in that case, then we take the new average, which is, I'm going to guess about 0.64 seconds. We multiply that by about 13.3. We got 8.512 seconds. Huh, okay. So that's actually a little bit of an overestimate. But it is more than 10. It's between 10 and 13, so this is kind of looking like, right? This is kind of looking like an O of n log n algorithm. And then hopefully this will finish in maybe 80 seconds or so, so a minute 20, right? That's our hope. Right? I think, maybe, possibly. Come on. I've been talking for about a minute. It should finish. Come on. Do your thing, loop. I just want one time to be like, haha. Almost there. Almost there. Right? I must have talked really fast or something. Or maybe it's just going to crash or something. Who knows? Oh, there we go. There we go. Perfect, right? So let's see. 0.7, let's say 0.75 is the average, or 7.5 seconds, times about 13.3. Okay, it still actually performs a little better. The expectation was around 99 seconds. So if the estimation, and it only took 89 seconds, so that's great. A minute 30. Felt like forever, right? Felt like forever to me. I thought it was never going to finish. So the point is that this tells you what algorithms are better for sorting, right? That's the point. I mean, that's not the point of Big O, but that is one of the first applications of Big O, is to tell you that quicksort and merge sort perform way, way better. If you have a list of size, say 10 million, are you going to do that list with a bubble sort or an insertion sort or a selection sort? No. Those are O of n squared sorts. So they're going to take a long time, right, to do a list of size 10 million. Whereas this algorithm, I mean, it does take time to do a list of size 10 million, right? It's not instant. But on the other hand, right, even though it's not instant, it's also not like a year. So, you know, this is a minute 30 rather than a year. So you can generally wait a minute 30 for your algorithm to finish. You generally can't wait a year unless you're doing some really important calculation. So, yeah. So that's basically the idea here. All right, so let's argue. The last thing I'll do today is let's argue a little bit that the Big O complexity of merge sort is n log n. What other reason is Big O important? It's hard to say why Big O is not important. I mean, basically, anytime you have an algorithm that has a large input size, you should consider the Big O complexity of the algorithm, because that'll tell you if it finishes in your natural lifetime, in the lifetime of the universe, or within 10 minutes, right? And that's it doesn't matter whether you're factoring numbers, it doesn't matter whether you're, factorization algorithms, matrix multiplication algorithms, tree search algorithms, everything in 341 that you're going to do, linked list algorithms, sorting, searching, just any algorithm in computer science, any solution to any problem. The question is always, what is its efficiency? What is the Big O complexity of the algorithm? Because if you know the Big O complexity, then you have... Will you have... certainly not. No. So I'm going to draw a picture that's going to prove to us that it takes about n log n time to do this process. Here we are. And then it's going to divide in half again. No, nothing in this class is going to take anywhere close to 10 minutes to run. I think my only point about the 10-minute thing is, like, 10 minutes is... You can do 10 minutes, right? You can live your life for 10 minutes while you wait for an algorithm to finish. You cannot wait for 82 years, right, generally for an algorithm to finish. This isn't like Hitchhiker's Guide where you can, you know, you ask a computer a question and then wait 10,000 years or a million years or whatever to get the result. We are humans with human lifetimes. And so we calculate the big O efficiency of algorithms in order to determine whether or not we want to wait around, or we can even wait around for the things to finish. So I know that this drawing might be a little bit messy, but I think it'll get the point across once I explain it. And I think it's pretty clear what I'm doing here. I'm just dividing these squares in half each time, which is, hint, hint, exactly what merge sort does. And so the question is, so we have two questions, right? How many subdivisions are there? How long does it take to merge the subdivisions? Right? And then how many times do we subdivide? And so remember that merge is an O of n algorithm. And so basically what that means is that at every step here, we are going to have one list of, this is one list of size n, so we have 1 times O of n, right? And then here, what we have is really 2 times the size n over 2, right? Which is also equal to n. And then we have 4 times the size n over 4, which is also equal to n. And we have 8 times the size n over 8, which is also n, etc. So no matter how many, so this is 16 times n over 16, which is also equal to n. So the total cost at any level of merge sort is O of n. But how many times do we subdivide, right? And so remember that we're subdividing in half each time. So if you divide something in half each time, then what you're eventually going to get is some equation like this. You're going to get 2 to the number of times is going to be equal to the list size n. And so in order to solve that equation, 2 to the number of times is equal to n, you need to take the log base 2 of both sides, and get something about like this. The number of times, right, t, or times I guess, because I've left it like that, is equal to the log base 2 of n. And of course now it sticks it all the way down there. So how many times do we subdivide? That number of times, right? So we take log base 2 of n, number of times. How long does it take to merge the subdivisions? It takes approximately n time, right? N, where n is the size of the list. So if you have 16 subdivisions, each of which taking n over 16 times to merge, that is O of n time, O of n time, O of n time, O of n time. So then overall, we know that this algorithm is, right? This algorithm is an O of n, an O of n log n algorithm, and I'll write it like this, I think. Just to indicate that we're taking the log base 2. So, and then we look at our experimental results, right? We look at our experimental results and we see, aha, right? Does it kind of match with an O of n log n expectation? And the answer is, yeah, basically, right? Like the proportion every time seems to be about, let's see, 0.64 divided by 7.6. Let's take the inverse of that, 1 over that. It's about 11.875, so let's see if 11.875 times approximately 7.6, that's approximately 90 seconds. So we see that it's taking about 12 times the amount of time, right? About 12 times the amount of time, which is slightly better than O of n log n in terms of like the exact computation of the factor. But remember that big O is just an estimate on the time. And so here we see that, but it does fit perfectly, right? It does fit perfectly because it shows that it's a bit bigger than 10 each time, right? Here it's about 0.5 here it's about 0.004 seconds, here it's about 0.05 seconds, here it's about 0.65 seconds, here it's about 7.5 seconds, here it's 88 point something, right? And so that tells us it's just a bit more than 10. So it's either an O of n algorithm that's a little bit inefficient, or it's an O of n log n operation that's performing a little bit better, at least on these sizes. And I would say it's, given the fact that we've just proved that it's O of n log n, at least theoretically, it is O of n log n. So the two O of n log n searches that you learn are merge sort and quick sort. And that's it for today, I think. I guess the only question is, like, if you're wondering what we're going to be tested on, I think maybe... I mean, of course that question is going to come up, right? I guess the answer is that you'll be tested on... it's hard to say. Because we used to ask people, like, just like, what's the big O complexity of this algorithm, and we'd give them 2 for loops, and people were saying, you know, n cubed, n to the 8th power, what's the best case scenario of quicksort? People were saying all kinds of crazy stuff. No one really, basically, we never really got very valuable answers out of this stuff. I think maybe some time estimation, time estimation stuff, that's something you can do. Maybe some very simple calculations of big O with like for loops and stuff. So it's like, here is an algorithm that has some for loops and some other things. This thing runs in what time? And the answer is going to be n times constant, so n squared, right? So that I can't say. I don't know yet because I haven't written it. Okay. So I know it's kind of vague. I'll try to make it a little more clear before the final exam. But I'll also try to make it something... My goal is to find some way to get people to actually be able to answer these questions without not being able to answer them at all. Okay. So that's all, I think. Yeah, in terms of, yeah, you'd probably guess that the thing is somewhere in the 900s of seconds. Of course, you'd have to run it. Now, of course, here's the thing. I'm going to re-upload this to the GitHub. You are all free to, you know, you are all free to download this file and to run it and test it out for yourself. Just put it on PyCharm and just start it going and leave it running for about 10 minutes or whatever, or 15 minutes or whatever it's going to take, and then something will pop out. Okay, so I might upload this thing. Let's reorder it so that it's a little bit more readable. I like to do it sideways for lecture, but then I think it's better to be vertical for PDF reading. Almost got it. Hopefully it doesn't crash. And then let's document properties, resize page to content, save again. Alright, I guess I'll upload this thing so you can have it. Okay. That's all for today. I'm signing off.